Good. Yeah, thank you. Thank you, Xiaodi, for the introduction. Thank you, everyone, for staying towards the end of this workshop. Really appreciate it. And some people who wake up early to attend Alexis' talk in the morning as well. So thank you all for staying through. So for me, so first of all, my name is Sheng-Tao again. I'm leading the algorithm application team at QuEra. So for my part, I will give you an overview of what one can do on neutral atom analog device, especially on Aquila, QuEra's neutral atom, first neutral atom analog device. I will show you, results on different applications areas so we can do on Aquila. Some of them done by QuEra and close collaborators, and some of them actually we are not aware of, like people who actually just use Bracket to access the machine directly, and we are not aware of as well. But for the talk, most part, I'm actually talking about what we've done and in collaboration with our collaborators. So yeah, I will start with a quick intro to Aquila, our analog device, and then in each of these areas, I will give you a kind of a taste of what we can do on Aquila in terms of applications in machine learning, in quantum simulation, and in optimization. And at the end of it, I will also give a very brief kind of what's coming on the digital side as well, and what's our plan going forward on the digital side. So what's nice is actually this talk is just after Pascal's talk, Hossein's talk earlier before lunch. So many of you might already kind of see a lot of this. I don't need to delve too much into details about how Ripper atom system works and on the analog and digital side. So I will skip, move fast on some of this part, but just very briefly, for our system, what's nice is for neutral atom systems, we can switch between analog and digital pretty easily. You can think about it's just using different atomic levels. And if we use one ground state and one Ripper state, we can put in the analog mode. And that will be, you have this Ripper interactions and then that has blockade effect and interacting. In the analog mode, we can position the atoms in various, like a lot of different geometries. This is actually a coastline of a word map, and we can put atoms in a position. So there's a lot of flexibilities in the analog mode for neutral atoms, and this is a hello world by just putting atoms together as well. So this is a real image of atoms. And on the digital side, I won't talk about too much today since this is more focused on beyond gate-based approaches. But on the digital side, we choose to use two states from the hyperfine manifold, and that will have long coherence time and in the order of second or even longer. And that one can do digital gate mode and only use a Ripper state as a way to entangling the qubits. Aquila, we launched our first machine, Aquila, on the analog mode 2 years ago, and just a few weeks will be 2 years old, 2 years old Aquila. So we'll be celebrating our, second birthday for Aquila. A lot of things happen during the time, and during these 2 years and before that as well. So this is really a collaboration with Bracket team from Amazon, from AWS. Aquila so far is still the only publicly accessible quantum computers based on neutral atoms. As far as I know, Pascal's machine is not publicly generally available. So this one you can use, just log in on Bracket and log in on AWS, and everyone will be able to use it. We have up to 256 qubits with flexible geometry, and as you saw in the previous slide, that we will really allow a lot of programmability in terms of the geometry, which will be good for for a lot of different use cases, and it's available for 130 hours a week. We added a number of new features this year: local detuning, tau geometries, and we're just looking at my time. Tau geometries and also tight geometries. These are new features we added this year. For some of the applications, we actually we'll make use of these new features as well. Applications in simulation, optimization, machine learning. There's a lot of exciting scientific publications coming out from many groups using Aquila. If you're interested, check it out on our white paper. it's not, there's some new features which is not in the white paper right now, the local detuning ones and so on, but it's still very well represented of the capabilities of Aquila, what we have, and the noise model and things on our machine. Very briefly, how it works. So we have 3 basic building blocks for analog Reaper atom device. They are atoms, so we use tweezers to trap atoms. Atom can, this is animation, of course. But it's a fairly accurate description. We have optical tweezers, we can trap atoms, we can move them around, and we have a ground state and Reaper state. Reaper state is a really highly excited state, and this representation of going to this high excited state of like the atoms electron cloud can be much bigger. Kind of nice analogy is actually you can think about feeding a coronavirus into an atom with a Reaper state actually. So it's actually a much bigger size than what the original atom is. And so it's in the order of 100 nanometer to a micro size, depends on the atomic level. And if atoms are far away, they can both be excited to the Reaper state. But if you move them closer, and this is the Reaper blockade effect, the Reaper state two atoms will be interacting strongly, and that will blockade both of them, preventing both of them to go to the Reaper state. That basically creates entanglement, and that's how we do gates as well with the Reaper system because of this blockade effect. For the analog mode, as I said, we have 1 ground state and 1 Reaper state. We drive, use a laser to drive between these 2 states, and this is our Hamiltonian, basically. The first term is an interaction term, which, N means if both states are in the Reaper state, they have a strong interaction with 1 over R6 decay. Second term and third term is a global drive, where we have Rabi frequency, phase of the laser, and detuning on top of it. These terms are a global drive we have in terms of control. A recent, as you can see, we have qubit connectivity. We can position the atoms almost arbitrarily. In 2D, we have coherent global drives and detuning term, which is kind of a Z term. Recently, as I said, we added this local detuning term as a new feature. This gives us more programmabilities here, where you can add individual weights to the atoms, to the qubit, and that adds a lot of new programmability you can use for different use cases, like for weighted graph optimization problem, or for machine learning encoding problem, and for quantum simulation, you can do disorder system and so on. So that's really an exciting new feature we added April this year, around April and May. Good, and this gives you a snapshot of what it looks like. We have atoms that are stochastically loaded, so they have around half or more than half. You can reach a higher fidelity, higher probability of loading the atoms, and then we sort them into geometries of user input. Let's say if you want the square lattice, we sort them with each of this is actually a measurement shot, like kind of. You can think about like creating a new quantum computer each time. Basically, with this reprogrammability, we actually put load the atom and sort them, create a quantum computer, and then we can run algorithms on it. With analog, for example, we run a global pi over 2 pulse. There will be superposition of 0 and 1. You have half probability measuring in the end after, and then you can put pairs of atoms. In parallel, they are very close to each other, so they can create a Bell state, and you can measure. In the end the Bell state. You can have half probabilities. You can even put more qubits within the blockade radius. Here is like 4 qubits. While within the blockade radius, you can create a 4-qubit like entangling gate, and then one of the qubits will be in the Reaper state, and that's basically how you can program this highly entangled state. If you have a many-body state which are close to each other, that will be a highly entangled state. Good. Just a quick overview of the new features I already mentioned. So local detuning feature, we can program disorder in the system for various applications. And you can use it to create different initial states as well. So before this, most of the time we just start with all zero state, and now with local detuning, you can create some other product states first, and then let it evolve and quench. So it's kind of interesting for a lot of quantum simulation examples as well. On the geometry side, we reduce the row spacing from 4 micron to 2 micron. This I didn't mention too much. So for our system, we actually atoms are live on rows here. So you can see each of them, they're actually well-defined rows, and there's minimum spacing between the rows. This is mostly, this is not like a hard constraint. It's mostly convenience for sorting. We can sort in parallels in rows. So that row spacing reduced to 2 microns, and the maximum geometry in one direction is also extended. Now we can fit in more atoms in one direction. This is also have kind of interesting applications in semi-1D system and 1D system. We see a lot of people, the researchers who want to do 1D system but need a longer chain, and this is basically enable that. And you can wind around, as well to have a longer chain as well. So yeah, so overall, these features continue to add new interesting applications, and we'll continue to add new features to our machine as well. Good. So that's a pretty quick introduction to Aquila, our analog quantum device. And let me go into a little bit of applications. Each of them is really a snapshot of what we can do on the machine, and this will give you a kind of idea of, basically the typical things. But there's always creative ideas that's outside of what we presented, what I presented here. One of the recent work we did is actually in machine learning. You can check it out on this paper here on arXiv. So for quantum machine learning, we know, I guess we know more about this the last 2 days. We have a Nobel Prize awarded in this area. So machine learning is really kind of, we call it unreasonably successful models. It's primarily data-based. Quantum machine learning is still an emerging field. A lot of researchers combining machine learning and quantum, and there are cases where quantum computers can potentially enhance machine learning models as well. And I will mention this a little bit later. Actually, some of the questions Carlton asked earlier about Pascal, I'll also briefly mention that why data is also like, how do we think about data? So yeah, on the data side, we know there's classical data, there's quantum data, and machine learning can apply to classical data. Most of classical machine learning, of course, is applied to classical data. But for quantum machine learning, of course, the primary use case at the beginning, we'll be thinking about quantum data. In this case, our work here is kind of it's classical data we did, but it kind of like this gives us some hints of, I'll mention later, even for classical data, which might have, what kind of data might have some hints which have quantum aspect to it, which might give rise to, quantum advantage, so-called, for machine learning. What are the challenges for quantum machine learning? So, there's variational quantum machine learning approaches, and we, by now, also Ed mentioned earlier today as well, there's problem with training and then parent plateau. There's always challenge for variational approaches. And on the experimental side, so far, the demonstrations are pretty rare and small and limited size, and also limited in think about advantage potential. So our work really trying to tackle some of these issues. So what's our proposal here? This is actually, start from classical literature. There's something called classical reservoir computing, which is popular in the early days before neural network really become a thing. And even for classical machine learning, it's still active research, and people are using for predicting, chaotic dynamics, for weather prediction and so on. Classical reservoir computing is still kind of used. So we extend the ideas of classical reservoir computing to quantum and using analog neutral atom device in particular. How it works is, imagine we have some classical data. We can do some processing of the classical data, down sampling and so on. And there are some feature vectors. We then encode the feature vectors into the quantum reservoir, our quantum analog device that can be encoded in different ways. In terms of we can encode into the position let's say each feature vector a number. We can encode into how far we move from the lattice. We can encode into local detunings, or we can even encode into global pulse in terms of time series data as well. So there's different ways to encode, and then magic happens. We just let it evolve, with a quantum dynamics that will create a highly entangled state, and then we measure the output. The output will be measuring 0 and 1s, and then we have a very simple classical layer. Here is typically what we use is a classical regression layer, and then and train the classical layer, and the quantum part we don't need to train at all. So this avoids a lot of problems with standard quantum machine learning. It's very trainable since we don't need to train the quantum part. It's only the classical part that's trained. It's resource frugal. It's noise resilient as well. The quantum dynamics is typically more robust than gate-based approaches. It's more scalable. We'll show like we can implement up to more than 100 qubits here, and then the classical intractability I will talk about briefly as well. Good. So that's the proposal, and what's the result on these approaches? We did this for a number of different tasks, and starting from the simplest, everyone use MNIST, like handwritten digit classification. Here, if we start from binary, try to distinguish 3 and 8, and it's a very simple task. These are different methods here. Classical is on the left. We have classical reservoir computing, 4-layer neural network, and linear SVM as well. This is the implementation on the quantum side. This orange bar is what we did on experiment with 120 samples. You can see it's very close to the simulation as well. So we did an exact simulation of 120. The results are very close, and it still differs a little bit from exact. If we have infinite number of samples, we can continue to increase the accuracy here. But with finite samples, this is what we got here. And we can do 10-class classification as well. So this is typically not as easy to do for multi-class classification here. You can see here, a simulation and the experimental result matches fairly closely. Of course, there's a gap between them due to noise and so on. But it's a fairly kind of a good representation of what's happening on the simulation and experiment matching together. Good. So that's a really kind of a very simple task here, and we move on to a different task. And other than classification, one can think about using it for time series prediction. This is what classical reservoir computing is used for a lot as well. One of the data sets we took is from a Santa Fe laser data set. You can think about this is a laser signal here, intensity, and you have some event happen, and the laser actually jump. This was used in the early days for time series prediction and standard data set. Here we explore a little bit different ways of encoding as well. So since it's a time series, why don't we encode in the time series of the pulse here? Right? Here is basically a detuning term. We encode the pulse here with our detuning and use that to predict the last point, basically, for the next point prediction. And experimental data and simulation actually matching the features in terms of the kernel of the quantum machine learning reservoir or kernel. On this, we show kind of simulation and Aquila result, and of course the original data matches closely to each other. Of course, there's still a gap because of noise, but overall it captures the qualitative result. We did a few, as I mentioned, different encoding terms here. We can think about local detuning term encoding. Let's see, it's blocking a little bit. So we have local detuning encoding, we have position encoding, and then we have global pulse encoding. And this is the experimental data, this is the simulation data. So the hierarchy of what works well actually matches pretty well to each other, and we know what happens. I can't go into too much details, but mostly is because of noise, because of the extent of the noise. For global pulse, for example, you have a pulse which is encoding the data, which is closer to long time dynamics, which will be decohered, and so that's why global pulse is actually less accurate, but in terms of local detuning and position, they're performing pretty well. Good. So, and that's kind of an initial test. We really try to scale this up. This we take another data set of a 3-class classification problem. This is from a Kaggle standard data set of tomato leaf. You can look at the tomato leaves and see whether they have some disease on the leaf and doing this classification. We downsample the data, and then we encode this grayscale and into positions of on the hardware, and then let it evolve and with a reservoir and measure it, and then train the classical layer. So you can see here, it continues to improve with the number of qubits, which is non-trivial actually. If you go in the scale of more than 50 or even more than 100 qubits, the performance continue to improve as the number of qubits is actually something that we didn't really expect at this scale. So this is the first, I would say, the largest QML, quantum machine learning experiment to date. 108 qubits we did at the largest. Prior record is close to 40 qubits. Google has a demonstration on quantum data with 40 qubits. In terms of performance with classical, we are now beating the best classical algorithm. That's obvious. So it's in between a linear, kind of a simple linear SVM and also a 4-layer neural network. If you continue the trend, maybe you'll beat one day, but of course, there's still more noise as well. So at this point, we cannot claim we are beating on classical algorithm. But how do we think about this? Is classical data, referring to Kelton's question earlier on. How do we think about there's any quantum advantage for classical data? And this, we really think a lot harder on this. And one thing we find out is actually this is based on earlier works. Think more about quantum reservoir, quantum part as a kernel, and there will be a classical kernel, there will be a quantum kernel, and potentially this quantum kernel, since it's quantum dynamics entangled state, you cannot simulate it. The quantum kernel is classically non-simulatable. Of course, there's caveats of tensor network and all of that, but this quantum kernel we can think about as a geometry, creating certain geometries, transformation of the data, and that will actually can transform in a way that classical transformation, classical kernel cannot capture. And with this, based on a work from Robert Huang and others, this kind of a method of, we have some classical data, but we can make use of this kernel geometry to relabel the classical data. So let's say I have a MNIST data set, and I just call the numbers a little bit differently and relabel them and create a synthetic data set. And that will have advantage to quantum machines. And you can see here the original data 3.8 classification. Quantum is not beating classical, like analogous classical reservoir computing. But if we create a synthetic data set, if we relabel the data set a little bit, and we can see actually quantum is beating the classical analog reservoir computing by a margin that's beyond the error bar. So this really tells us it's possible there is potentially some data set, even though classical, that one can have quantum advantage, and we call it comparative quantum kernel advantage. And this only compared to certain classical algorithms side-by-side comparison, but still, it works on the machine, and we show that there is a advantage in terms of on this synthetic data set. So the question is, then how do we find this data set? That's still an open question. That will be for future explorations. And here we really show there exists some data set. If we're given by, if we don't do this synthetic processing ourselves, if we're given by this data set, and then you can actually see quantum computer can do better than classical. So actually, how many minutes do I have? 5 minutes or 10? 5, good. Okay, So yeah, so this is on the machine learning side. If for those who are interested, student postdoc, we have the paper, and also we have the code, tutorial code as well on these links. Feel free to check it out. On the machine learning side, there is also like other works I'm not mentioning here. There was a talk on Monday by Terhat from Rice as well. I think some of you might be here. And this is also they use Aquila to do generative machine learning, which is actually very interesting. What we thought about, but didn't have a chance to do yet. So it was very nice to see they use Aquila to do generative machine learning, like a adversary GAN, quantum GAN. Good. So I'll move a little bit faster on the rest. On the simulation side, so a lot of this pioneering works are done by Harvard and also by Antoine Broadways and others, Manuel Andres from others. This is for quantum simulation, kind of exploring the exotic phases of matter, whether it's ground state, whether it's dynamics, and there's earlier works at Harvard by doing this kind of a 2D checkerboard lattice and seeing some phases of striated phases with usual quantum phase, and then doing the spin liquid implementation as well. We reproduce part of the result. You can see here and check it out as well on the white paper. Reproduce some of the checkerboard phases, and on the right is quantum scar dynamics. It's also very interesting dynamical behavior here. There's a lot of ongoing works, both internally at QuEra and also in collaboration with others. We do in this quantum simulation direction. We have a collaboration with Peter Zoller's group on stream breaking. Alexei actually mentioned in the morning, with Chris Monroe's group, there's a parallel paper, and there's a paper from Google came out earlier as well. So there's 3 parallel papers on stream breaking that's coming out very soon from our collaborations. We have working with Purdue and Bracat on this just tree Switzerland model, which will be the next talk. You'll hear much more about this second work, like this kind of a geometric frustration, which is actually close to what happened in materials. And we have some proposals on trimer spin liquid. Earlier this year, we have a quantum floating phase exploration. This been predicted theoretically. There's a in the 1D system, there's a floating gapless phase, but have not been observed experimentally. So we did the implementation on Aquila and actually observed this gapless phase, some signatures. And then, we have collaborations with NERSC as well. This 2 collaborations thinking about with NERSC. We have projects on false vacuum decay, quantum dynamics. This is also similar to what Harvard has done on coarsening and so on as well. So that's on the simulation side. That hopefully gave a kind of a very quick overview. On the optimization side, I won't talk too much as well. This Hossein from Pascal actually mentioned some of this earlier. A number of years ago, we proposed this maximum independent set problem. Actually, this is one of the work I did as a postdoc at Harvard. Basically, the problem is, we want to find the maximum number of nodes which are not connected to each other in a graph. And that can map naturally to Ripper blockade physics, and we actually did an implementation together with Harvard now 2 years ago, up to close to 300 qubits, and observe a quadratic speedup, like compared to like classical simulated annealing. This is based on actually coherence, and there's many reasons. There's actually like some deep reasons why we could observe this coherent speedup. I may not have time to talk about that a lot, but I'll be happy to talk offline as well if anyone is interested in this. We reproduce some of this on Aquila as well. This was initially done at Harvard, and this, you can just program it on Aquila and implement with it as well. There's some code there if anyone is interested. And a number of works, further research works on optimization side. Hossein earlier from Pascal said, like, the gadget is actually challenging if you want to do, beyond maximum independent set and using gadgets to do it. So that's challenging. Actually, we agree with that. We are thinking about other ways to optimization, basically treating the quantum computer more like a sampler and that put a lot of work in the classical part, but using quantum potentially as a sampler to aid classical optimization results. So we have one of the paper there, and for other ideas beyond purely adiabatic algorithm, there's a paper from Ignacio Ciar's group on the theory project first, and then we did a implementation together. Just think about, for some problems where the gap is very small, if you do adiabatic algorithm, for some problems, the gap can be exponentially small and even super exponentially small. But adiabatic will not work unless you have a exponential coherence time. And some method to prevent this is basically a shortcut to adiabaticity. You can do a quench sweep algorithm. The quench will actually excite some of the excitations to excite the state, and then you actually go down to ground state. So that's kind of an interesting demonstration here for optimization. And there are other works. QuEra is not involved at all. BMW and AWS have used Aquila to do some optimization work on recursive optimization, and also quantum informed recursive optimization, and also using kind of a designing better hybrid algorithm as well using Aquila. Good. So that's I'll wrap up quickly. So that's kind of hopefully give a good overview of what we can do on our analog machine, and maybe give some inspirations of what's more to come as well. On the digital side, very quickly, our architecture on the digital side, this is you might see some of this paper from Harvard as well. We have different zones of storage, memory, and gate zones as well. We can move the qubit coherently, and this is actually actual atoms we move coherently. And here you can think about designing gate sequences, and how do we compile that into moving atoms? So that's a very interesting problem we're tackling. This gives out a lot of advantages in terms of long-range connectivities and so on. So it's very super exciting. Lastly, just to show our plan, we have Aquila last year and this year. This year we added new features on Aquila for our analog device. We also have a gate-based machine, which is like operational and ready to use. Where we started some projects on our gate-based machine as well. Stay tuned for some results coming out this year. And next year we're really moving more towards error correction as well. Think about larger scale and with logical qubits. The goal is to reach 100 logical qubits by 2026 with more than 10,000 physical qubits. And this, of course, depends on a lot of details, how you do, of course, error rate as well, logical error rate, and what kind of code you want to use and so on. But this is very high level. Good. With that, I would like to end. For student postdocs, we are hiring. If anyone is interested, please check it out. We just had our 5-year celebration at QuEra. QuEra, we are 5 years old. For a lot of this Aquila use for the analog neutral atom device, you can check it out on Blockade. This is our SDK, which we use as a simulator, also as a way to program our device. With that, I think I'm running out of time, and thank you all for your attention.
Thanks a lot for the overview. I wanted to ask hopefully a quick question about the gate, like where you showed the atoms moving around.
Mm-hmm. Yep.
So is my understanding is that you, in the analog regime, you're coherent for about 4 microseconds.
Yep.
And so with what proportion of that time will be spent moving things around? And
I
then
see.
how much what gate depth could we hope for with this type of?
That's actually something good to clarify. So for analog device, we limit to 4 microseconds. Our coherence time is a little bit longer, but that's the right time scale. For the digital, this is more of a digital use case. And the hyperfine state, their coherence time is actually in the order of second or 10 seconds even. So there's a lot of room you can move qubits around and doing gates and so on. So coherence time is really not the limitation for neutral atom or for ions for the same reason as well. So here, the move is more in the order of 100 microsecond. So the querying time will be like second. So you can do a lot of move during that time.
Thanks.
Thanks for the talk. I want to ask about this reservoir computing and machine learning part. I wonder, so in some quantum machine learning task, actually there's some bottleneck that people need to put this classical data into a quantum device.
Yeah.
I wonder for this reservoir computing case, is that also some issues there? And also if we consider this, whether this quantum advantage, you mentioned that to what extent you still expect that? Yeah.
Right, yeah. Yeah, thank you for that question as well. So that, yeah, we avoid that, basically this data loading problem in terms of if you're talking about QRAM and so on. So we don't need to start with a highly entangled state and kind of like loading the data. Here, basically, the classical data is loaded into classical control. You know, the position of the atoms or the local detuning term, those will be encoded in the Hamiltonian terms. And you just let it evolve as a Hamiltonian, so creating a entangled state, and you try to extract the information in the end. So in this case, the classical loading is very simple and very easy for us.
I see. Thanks.
Thanks. I also have a question about this. Have you also thought about sort of predicting quantum time series?
Oh. Wow, yeah, that's an interesting question. So we certainly thought about that, but we haven't done anything on that front yet. Yeah, quantum data is definitely one of the interesting areas. We started from classical data here, but for quantum advantage, it's natural to think about quantum data. One thing to think about is how do you actually encode the data? Whether you start from some entangled state and like try to predict the phases, and so there's theoretical works on that, but we haven't done that here.
Cool.
Hi, I just have one question about optimization. So I think you briefly mentioned a paper where there are some approaches to non-native optimization problems. So are you talking about optimization problems that are like not in the form of MIS?
That's right. So here, please check it out on this paper. Here we actually treat more like a sampler. So actually you can even go beyond binary kind of like data, basically discrete data. So here for them as an example, we can, let's say we treat the quantum as a sampler. We measure the output and measure some correlations, and we take the correlations to fit into some classical pipeline and use the correlations to kind of further optimize the classical problem. So this whole loop, we have basically a few prototypes there. It's still questionable how generalizable this is, like whether we can tackle all the problems, but this hopefully actually gives some ideas of thinking about beyond just MRS for River system.
Thank you.
Hey, great talk. Quick question for you. I think you had mentioned that there was some sort of protocol for avoiding issues with exponentially decreasing gap sizes. I was a little bit curious if you could elaborate more on how well you're able to get around with your exponentially decreasing gap.
Yes. So yeah, so this is actually this work, which I just talk about. Check it out here. So the quick, very short idea is, if the gap is exponential, if you do adiabatic, you will go to excited state. But if you are smart about it, you can try to do a quench before the gap. The quench will bring some excitations coherently to some of the excited state, and then the excited state actually can come down to ground state after the gap. So it's really kind of a shortcut to adiabaticity. It's in terms of generally applying this, it still will be a challenge, but we see in some cases that actually this will help a lot. In this paper, we basically show for this kind of simple toy models, we see actually doing coherent quench. We have a quench here, and then that I will actually kind of like avoid this exponentially gap and go to some excited state and come down, basically.
So in order to take advantage of that, wouldn't you effectively already have to be able to solve the problem that you are encoding on your device? Because otherwise,
no, not necessarily. That's also a good question to clarify. This kind of quench area, we can do it. We can actually try it at different time without knowing where the gap closing area is. Of course, it would be better if you know where the critical point is, where the gap closes. But you can try to quench at different time, and so we actually the quench time and duration and height are all kind of variables we can pick.
Yeah, I like this idea quite a lot.
Yeah.
Like in the adiabatic community, there's kind of this belief that we'll never know where the smallest gap is.
Right. Yeah.
Otherwise, we would do things like adjust the schedule to
Yep.
slow down during that critical gap.
Yep. Mm-hmm.
So, I'm actually probably I love all these types of heuristics, but maybe a word of caution. The theorists in the adiabatic community have been saying nope, that's not a viable strategy to solve our problem.
Right. So to a certain degree, I agree with that. If you really go to large scale, if you don't have signal at all, across all of this, and if you don't have enough coherence time, then it doesn't work. This is really in the scale of, you're still within the coherence time. You can try to optimize a little bit here, where, again, I don't need to know where the gap is. I can measure at different point, and here will give me information. Here, if I quench at this point, I'll have higher probabilities here. I suddenly see a ground state here, a better ground state. That will give me signal, oh, this is working at this size. So it's really trying to more empirically go beyond adiabatic algorithm. But I agree, I'm not claiming this you can work magically, at large scale. And so, yeah.
Yeah, I think just in the interest of time, we should just stop here. Thanks, Sheng-Tao, again for the talk.